Go ahead.
Good morning, everyone. Welcome to the first lecture of the workshop of the PWF Sudan, the second edition, DFT methods and applications. Today's lecture will be given by Professor Matteo Gatti. He's the group leader of the theoretical spectroscopy group in ICAL Polytechnic and a member of the planning committee of the African School on Electronic Structure Methods and Applications, ASISMA, and also by Fatema Mohammed, a Eurotic Marie Curie postdoc in the theoretical spectroscopy group at the ICAL Polytechnic and a lecturer at the Khartoum University. She is also a member of the executive committee of the African School on Electronic Structure Methods and Applications, assessment. It's a pleasure to welcome you today to the workshop, and the stage is yours. You can share your slides and start. I will stop sharing.
I unmute and then
No, you're not muted.
I was muted, but just I unmuted myself now. Yes. Hello. Yes. So full mode. Yeah. So I'm sharing the slides in the full mode, right? Okay. So can you hear me well?
Yes, we can hear you very well.
So assalamu alaikum. Hello everyone. Thank you so much for the opportunity. I am happy to present this talk together with Matteo. Okay, so the idea is to give something brief about quantum mechanics. Okay, you know that quantum mechanics can be taught in more than one semester, but what we have tried is to find out things that are that can be useful in order to learn DFT. Okay, but we are not going to teach you all quantum mechanics in 3 hours. Okay, so as Ala introduced me, I am Fatima, and I am going to present this with Matteo. So I am a staff member of the physics department at the University of Khartoum in Sudan. I am also currently a postdoc in Mattheo's group at École Polytechnique here in France. So I'm going to present this like a brief let's just say lectures in quantum mechanics. Okay, so so here are the outline of the talks. So of course, when we talk about quantum mechanics, the fundamental equation in quantum mechanics and the universal equation is the Schrödinger equation. Okay, and then I will take a very simple example in order to see how we apply quantum mechanics or how to apply Schrödinger equation and solve a quantum problem. And as an example, I will use the simple harmonic oscillator. Okay, and then I will throughout all these things, I will try to introduce to you to some concepts they are useful, like the wave functions, like eigenvalue, observable, and all this kind of stuff. And then I will just introduce the many body problem in quantum mechanics, and then it will be followed by Matteo, who will talk more in details about the many body problem, which is the things that you are interested in throughout this school. Okay, so to start, I would start with the claim or the hypothesis that De Broglie taught us, or he claimed in his PhD thesis, that any object can have an associated wavelength. Okay, and and in which the de Broglie wavelength is given by this relation in which there is this inverse relation between the wavelength of an object and its momentum, okay? And we know that for large objects, like can be like what we have learned already from the, let us say, introductory course for quantum mechanics, that objects that are large, like human beings, car, or whatever, they have a very tiny wavelength. That is why their wavelength is not relevant, or they are irrelevant. But if we talk about a tiny object like electrons, so their wavelength becomes large in a sense that they are comparable to let us say interatomic distance in crystals. And in this way, we can observe diffraction or interference, okay? Which these experiments predict that electrons, they have can have also wave nature, okay? And then, so we have this matter wave that was introduced by de Broglie. Then to define or to understand more the wave nature of these matters, Schrödinger came out with its famous equation that we called Schrödinger equation, okay? And then here I am going to present the Schrödinger equation for one electron, for example. Then the general form of Schrödinger equation is usually written in this way, okay? So we have a Hamiltonian, which is an total energy operator that acts on a wave function. And this is a wave that, let us say, that proposed by de Broglie, let us say, and is equal to, and this wave function can evolve on time according to this right-hand side in the equation, okay? So, and this wave function can be a function on space and time, okay? And yeah, it can be like an object like this. And for a single electron, we can have the total energy operator, or what we call the Hamiltonian, can be written as a kinetic energy operator, which is this first term that have the Laplacian here, and a potential, okay? So if we, let us say, consider an electron in a potential field, then we can have, this electron can have kinetic energy, which is this one, we call it the kinetic energy operator, and then it can have a potential, which is this one, okay? And then we have this one, okay? This is an external potential. It can be Coulomb interaction or whatever, we will see again later. And then this is a time-dependent Schrödinger equation. Why it is time-dependent? Because we have a potential that depends on time, okay? That is why we call it time-dependent Schrödinger equation. But if we have an static potential that does not depend on time, that if we can like say that V of R and T is only a function of space coordinate, then we can take our wave function or the solution of the Schrödinger equation and write it in this form, in which we have a function that only depends on the like space coordinate times another function that depends on the time, okay? And if we are able to write our solution in this way, then we can put it back in our full Schrödinger equation for one electron, and then we will be able to decouple this equation, the full equation, into two different equations. In an equation that depends only on the, let us say, on the electron coordinates on the space, okay? And another equation that depends on time, okay? And then in this way, we will have this operator, which is a Hamiltonian, acting on the wave function, is equal to an eigenvalue, which is the energy that acting on the wave function. And this is what we call the eigenvalue problem. And this is what you usually solve, or this is what we are interested in to solve, okay? So this is the eigenvalue problem of the Schrödinger equation, or the time-dependent Schrödinger equation, okay? So, so if we have this eigenvalue problem, okay, and if we solve the eigenvalue problem, we can get our wave function, okay? So the solution for the Schrödinger equation can give us the wave function. This is something similar, like if we, in quantum mechanics, in classical mechanics, when we, let us say, solve the Newton's second law, okay, we can get the let us say the trajectory of the particle, right? So for example, we can get the position, and from the position we can get the velocity, and from the velocity we can get let us say the momentum, right? So like if we solve knowing the force, then we can get all the information about the particle. So in quantum mechanics, if we solve the Schrödinger equation, then we can get the wave function. And the wave function describes the state of the particle, okay? It describes the particle, okay? So, but the wave function itself has no meaning, okay? Like in the quantum, let's say classical mechanics, we can define the trajectory of the particle. But here, if we just get the wave function, it doesn't have a physical meaning. But what it has more physical meaning is the probability, okay? And this was the Max Born interpretation for the wave function. And what we like have here is the what we call the probability density of the particle, okay? For example, here at position R, okay? And then let us say if we find like more probability distribution, let us say, for example, around the nuclei, it means that most likely the electron are present around the nuclei, okay? And let us say if we want to define the probability, so we have the probability density. So it's just like when we have the probability to find the particle within, let us say, a given volume should be defined in this way, okay? So we have the modulus square of the wave function multiplied by the d cube of R, okay? And since if we have the particle should be somewhere in space, okay, it means that if we integrate over all the space, okay, then the if let us say, suppose that we have one particle, then if we integrate over all the space, then the integral over the probability should end up to 1. Sorry. Yeah. And this is our, let us say, normalization condition. So the normalization condition means that, let us say, the particle has to be somewhere. I don't know what happened. So the particle has to be somewhere, okay? So it means that if we take the limit of the wave function at the edges or at x equals to infinity, this supposed to go to 0. So we should have like a well-defined equation like what I show here, okay? So so now if we want to like solve a very simple quantum system using the Schrödinger equation, as I said, we can consider the simple harmonic oscillator, okay? So why am I using the simple harmonic oscillator and not something else? Because the simple harmonic oscillation is a simple quantum system that we can solve, and it describes many things. Let us say we have, okay? For example, if we have two atoms, okay, that are linked with a string, let us say, then these two atoms, if we look at their potential, okay, at the minima of the potential, they have a parabolic like shape. So it mimic, let us say, the harmonic oscillator, okay? Their potential mimics the harmonic oscillation around the equilibrium, just like because for the harmonic oscillation, we have this potential that is parabolic, okay? And for example, also if we have lattice vibrations, okay, like phonons, and many oscillatory system, they mimic the harmonic oscillator. That is why the harmonic oscillator could be a very good approximation for them. That is why we choose to present this quantum system that is the harmonic oscillator. So we know that from classical harmonic oscillator, the total energy of the system can be given if we have, let us say that we have a particle that is attached to an spring, okay? So this particle can have a kinetic energy, which is p squared over 2m, plus a potential energy. If we make a small displacement, then we have a force that is act on this particle, okay? And the potential is related to the to this x square, okay, where half m omega is all constant, okay? And then if we want to write the quantum harmonic oscillator, then we can write our energy will be the Hamiltonian, okay, which is the operator, and then we have to write the momentum and the space in the operator form, okay. And the momentum in the operator form in quantum mechanics can be written as this one, minus I h bar d by dx. And then the position operator is just x, okay? Then we can have our energy operator can be written in this way. Can be written in this way. So can be written in this way, that we have a kinetic energy operator, which is the contain the derivative square, and then we have the other term, which is the potential term, okay? And then what we want to do is to solve this eigenvalue problem. So we have our operator, which is the Hamiltonian, which is h, and then we act with it on the wave function, which is psi. It gives us the energy for the harmonic oscillator times psi. So our unknown in this equation, in this eigenvalue problem, are the wave function, which is psi x for the harmonic oscillator, and the eigenvalue, which is E, our energy, okay? So what we want to know, what are the energies and what are the wave function for the harmonic oscillator. So we know that a Schrödinger equation can have a solution for each value of the energy, okay? So if we put for any value of the energy, we can solve the Schrödinger equation and we can have a solution. But as we said that not all the wave function are acceptable. So the only acceptable wave function are the one that has to be normalized, or their integral must be equal to 1, okay? Or they should be normalized or normalizable, okay? Then it means that we want a wave function, a solution that when we take the limit as x goes to infinity, it should be constant, or it should goes to 0, okay? Because only these solution are the one that will give us a normalized wave function. It means that in this case, we cannot have only specific energies, but we can have a quantized energies. And here I give you a very simplified way to understand this. For example, if we choose an energy, okay, then we try to solve Schrödinger equation for this energy. Then we obtain a wave function, okay, and then we see if this wave function can be normalized. If yes, then we accept the energy. If no, then we reject this energy. In this way, we obtain only allowed energies, which are for the harmonic oscillator are given in this way. So E of n is equal h bar omega times n plus half, okay? And these are, let us say, a fractional of h bar omega, and n is the quantum number that we know, okay? And then for each state, then we have a corresponding eigen function, which is given in this form, okay? So here we can see our potential for the harmonic oscillator, which is parabolic, okay? And these are the energy levels, okay, that are defined here. We have the zero energy, which is half h bar omega, and then we have the other energy levels that are well separated, and each one of them has a given solution for it, okay? And yeah, okay, so this was for the simple harmonic oscillator. Now that we have the wave function, okay, what do we want to do? Our idea is to compute observable, okay? Observable are things that are things that we can measure experimentally. And actually, we want to solve the Schrödinger equation, obtain the wave function, and from the wave function, the main purpose of solving the equation is to calculate also observables. Okay, so for if we have, for example, for a general operator, okay, which is I call it Q. Okay, how to calculate observable? Observable is the expectation value, which the Barrow enquete that you know from quantum mechanics, also can be written in the integral form in this way. And then if we integrate over all space, this quantity, which its expectation value can be written in this way. So we have the wave function, and then we have the operator acting on the wave function from the right, and also in the expectation value form, in the expectation form can be written in this way. So let us say if we want to calculate the kinetic energy of the particle, how do we calculate the kinetic energy operator? So we know that the kinetic energy operator for the, let us say for a particle in one dimension, is in this form, right? So we have this. And then the expectation value, we just take the formula that I have introduced in the previous slide, and then we put our operator here. And then this also, if we take the integration by part, can be also written in the way that I have on the right side. Then if we use the wave function that we have for the harmonic oscillator, put it in this equation, then we can calculate easily this integral. And then we calculate the expectation value for the kinetic energy, which is the half of the total energy. And then similarly, we can also calculate the expectation value for the position. Okay, so in this case, the position is just a multiplicative of the wave function, so it can be taken on the left side here. And then, of course, the energy is conserved. So we have the expectation value for the potential is also equal half of the total energy. And then we can also calculate the total energy of the system by summing the expectation value for the kinetic energy plus the expectation value for the potential energy, and we get this. Okay, so it means that once we have the wave function, then we can calculate any physical observable. Okay. Yeah. So yes, now this all is very simple. So the harmonic oscillator is one of the few problems that we can calculate analytically. Okay, and so now we will come to more complicated problems. Okay, am I very fast? Is good? Slowly. Yeah, okay. So now I will introduce our real system, which is the system that we are interested in. For you are interested in for this school, okay? Which is the, let us say, if we have a crystal or we have a system that is formed of the electrons, of nuclei, and these things, okay? So now we want to, let us say, solve the Schrödinger equation for this system, okay? So if we have a material, and then if we try to write Schrödinger equation for a given material, okay, which is the Hamiltonian is generic, okay? And then we are able, if we are able to solve the Schrödinger equation for let us say for a given material or for materials, then we are able to understand these materials, okay, at the atomic scale, okay? And this is what we are going to do. So let us say if we have nuclei and we have electrons, then the Hamiltonian of the system can be written in terms of the, of course, we will have the kinetic energy for the electrons, which is this, the kinetic energy operator, which I call T hat here. And then we can have the interactions between electron and nuclei. So, and this is what we call V hat. And then we can have interactions between electrons themselves. And this is what we call V electron. And then we can have interactions between kinetic energy of the nuclei itself. So it is Tn. And then we can have also interactions between nuclei themselves, okay? Which is what we call VNN. And we know that the kinetic energy operators in 3 dimensions For the electrons and for the nuclei, they are contain this Laplacian, okay? So we sum over each electron, so that is why we have here sum of I over I small, and then we also have the kinetic energy for each nuclei, so we sum over all the nuclei, okay, in the system. And then we have the Coulombic interaction between electrons and nuclei, okay? So we have this Z, which is the atomic mass for the nuclei, over Ri minus R capital I, which are the coordinates of the nuclei and the coordinates of the electrons. So we have the interaction between each electron and the nuclei. And then we also have the interactions between the nuclei. So it is also this Coulombic interaction. And this interaction is repulsive. That is why it is positive here. And then we have the interactions between the electrons, which are given in this way. So it is the Coulombic interactions between the nuclei, between the electrons, in which we have differences between the electron coordinate. And then here we also put this fraction half, so that we don't count interact the interaction twice, okay? And you can see that here all these terms are positive, except the interaction between the electron and the nuclei. So this is the only thing that is the attraction term, which hold the, like, is the main term that is responsible of having our, let us say, the distribution of our crystal, and it is the one that also distinguish one system from another, okay? It is the way that how the atoms are arranged on the crystal, okay? Then we have here our Hamiltonian, or we have our total energy operator. What we can do is to use the eigenvalue problem of the Schrödinger equation, in which we have it here. So we have the Hamiltonian, which I defined here above, and then we have the total wave function. In this case, the wave function is not like what we saw in the harmonic oscillator. Its symbol is just 1D, okay? So it was, if psi was a function of x, but here we have, if psi is a function of electron coordinates, which we call Ri, and in the atoms we can have many electrons, so it is the coordinate of all the electrons, and we have Ri capital, which is the coordinates of all the nuclei, okay? And this is the total energy of our system. So what we want to do is to take out the Hamiltonian, put it here, and solve this equation, and then get obtain the wave function, and solve this problem, okay? And then we can calculate any observable that we want for the system, okay? So but this is not very easy. Why is not easy? Because this wave function is very complicated, okay, to obtain, okay? Because, and we cannot do what we have done. You remember when we have shown that when the wave function, when we wanted to decouple the full Schrödinger equation and obtain only the Schrödinger equation that in which we have the time independent Schrödinger equation, we were able to write the full wave function in terms of a function that depends on the space and another function that depends on time, right? But in this case, we cannot simplify this problem. We cannot write the full wave function as a function that depends only on the coordinates of the electron time a function that depends only on the coordinate of the nuclei, because the electrons and the nuclei are coupled with this term, which is the attractive Coulomb interaction between the electron and the nuclei. But how can we simplify this problem? We can simplify this problem by considering what we call the Oppenheimer, or the adiabatic approximation. And the idea of the adiabatic approximation is that since the electrons are much faster than the nuclei, okay, then we can write the total wave function in the, because of the mass of the electrons is much less than the mass of the nuclei. Taking this into account, we can write our the total wave function, which is a function of the of Ri small and R capital, as a function that depends on the has, let us say, has more quantum nature on the nuclear electrons coordinate time a function, and where there is less, let us say, less less effect on the atomic, let us say, coordinate time another function that depends on the only on the atom's coordinate, okay, or on the nuclei coordinates, okay. So this itself is not an approximation. We can in principle be able to write the full wave function as a function that depends on the more on the electrons coordinate time another function that depends totally on the nuclei coordinate. If we take out
I have a question here, if it's possible.
Yes, sure.
It's because it's very critical to understand when you mention coordinates.
Yes.
So what do you mean here specifically when you say coordinates? Is like just the
I
three
mean
dimension of the coordinate, or how do you specify the coordinates?
So I mean by it is electrons coordinate. So it depends on the number of electron for your system. So you have, let us say, 3 electrons, then you have R1, R2, R3, and then you have, or what do you mean? Yeah, you did.
Is there any like way where you have to specify the type of the coordinates, like what's the dimension, for example, or?
Yeah, so each coordinate is each let us say particle is represented by let us say by R, and R is in 3 dimensions. So you have X, Y, Z. So let us say particle 1 is R, we call it R1, and particle 2 R2 is undefined, and particle 3 is R3. And then of course we have electrons, they are not distinguishable, but then we have 3 electrons, then we have 3 coordinates. We have 4 electrons, we have 4 coordinates, and so on.
Okay, thanks.
And the same for the nucleus, okay? And then if we take this wave function and then we put it back in our, sorry, I will go back just for the previous slide. And then if we put it back on the eigenvalue problem of this equation, and then we write our Hamiltonian, and then try to calculate this equation by taking the expectation value for each term, then we will be able to simplify our equation from an equation that was having all those terms that I have defined, okay, that depend on the that we have the kinetic energy of the so we will come from this equation that has also kinetic energy of the nuclear interaction into this more simplified equation, okay, because when we put back the wave function that was proposed by Oppenheimer into the equation, then then there will be an approximation in which we can take out we can cancel some terms that depends on the nuclei, okay, and then we will end up in this more simplified Hamiltonian, in which we have only the kinetic energy for electrons, and then we will have the interactions between electron and nuclei, and then we will have interactions between electrons. And we can see that in these equations, we don't have we don't have the kinetic energy of the nuclei. We only have the kinetic energy of the electrons. That is why, but the nuclear coordinate appears here in this column attraction term. So in this case, we have a, so if psi of r at the function of r, which are the coordinates of the nuclei, so we have a Schrödinger equation for electronic Hamiltonian for a fixed nuclei. So for a fixed nuclei in space, we then solve the Schrödinger equation, and then we obtain the wave functions that are associated to the electrons. Okay, and that is why we call this electronic Hamiltonian. Okay, so using Born-Oppenheimer oscillation, we can decouple the full Hamiltonian into two Hamiltonian. One Hamiltonian that has to do with the nuclei, and another Hamiltonian that has to do with the electron. And since our main idea is to understand, let us say, the electronic properties of the system and so on, then we are interested only to solve the Hamiltonian or the Schrödinger equation that has to do with the electrons. So we solve the electronic Schrödinger equation, which is given by this one. Hopefully I was clear. So yeah. So so once we have our Hamiltonian, which is this one, and then we have this is the equation that we need to solve, then we can solve these equations. If we get the wave function in principle, then we can obtain what we call observables. Okay, this is what we want to calculate usually in quantum mechanics, because they are something that we can measure and then we can calculate. Okay, so observables I have already introduced, but maybe I introduce again. So they are expectation value of the operator. Okay, and here our operator is the Hamiltonian. Okay, then if we take the expectation value of the Hamiltonian in terms of this wave function, then we can get our eigenvalue. And the eigenvalue is our energy, for example, in this case, the total energy. And the total energy, it means that it should be calculated in terms of the wave function, okay? That is why we need the wave function in order to calculate the total energy. This and because E can be written in terms of psi, and psi itself is a function of the space coordinates for the electrons, it means that this E of psi is a functional. And a functional, you will hear a lot in DFT, is and also for you, Matteo, right? So a functional is a function of a function. So if we have a function, then we have when we have a function of a function, then this is what we call a functional. And so the input is a function for this functional, and the output is a number. So when we calculate this, we will get a number out of it. Okay, and then for a generic observable, then then we will have the expectation value for this operator, which is supposed to be calculated in this way. And in integral form, we will have a more complicated integral than the one that we saw in a single harmonic oscillator, because we have many coordinates in this case. So we have depending on the number of coordinates we have, we will have a multiple integrals in this way, and this is what we need to solve in principle in order to obtain our observable. Okay, and so is there any way, because this integral is very complicated to be solved, but you will see in DFT that there is other ways that we don't need to calculate this complicated integral in order to obtain observable, but there is another way that you can be able to calculate the same observable without going through this complicated way of doing it. Okay, and this is what you will see in DFT. So I will stop here, I think, and then I will pass it to Matteo, so he will tell you some ways in which we can solve the many body problem, which is the electronic Hamiltonian. Okay, and then here I have some suggestion for references. So this is a very good reference, in which you have the Physics of Atoms and Molecule by Bransden. You can have a very brief introduction to quantum mechanics. You can also have the how they solve quantum mechanics for hydrogen atom, which we have one electron for two electron system, and then for many electron systems. So is a very good book to follow. And if you have other references, can be also this electronic structure book by Richard Martin. And if you want to, of course, you will not be able to learn DFT in one day, but if you want to have like a full course on DFT, I could also suggest this Coursera course, which is very good for an introduction in DFT. And
It's available online.
Thank you so much, Fatima, for the lecture.
YouTube,
I
Online.
would also,
it's available online also. Okay, yeah.
sorry to interrupt you. Thank you so much for the lecture. And I will ask the participant, if you have a question in the first part, you can ask now.
Yes, yes. So was I very fast? Was it okay? Okay.
No, it was good.
Yeah, okay. Yeah. Yeah.
Any question? If there is no question, we can start or take a
So I
break.
think what I have introduced is already simple, and most of you have, all of you, I think, have seen it in your introductory course in quantum mechanics. But maybe what Matteo is going to introduce might be like new for some of you. Yeah.
Okay, thank you.
You're welcome. Yeah.
We have one question by Ahmed.
Yeah.
Ahmed Mu'tas.
Okay. My question is about the potential energy. From classical physics, I know that potential energy is related to the height or the position of the object, and it depends on the gravitational force. How the potential energy in atoms has an effect.
You mean how do we?
Yes, I mean how do potential energy affect the movement of electrons around the nuclear?
So we count only the interactions between the electrons and the interactions with the nuclei, and this is already not an approximation, no? So we don't count the, yeah. Okay.
Maybe I can also jump in. This is actually a very interesting question. And actually, gravitation is not included in quantum mechanics in the sense that gravitation from the general relativity of Einstein and quantum mechanics are so far not compatible. So people are actually working, it's an open field of research to combine the two. So how to combine quantum mechanics and gravitational physics is still an open field of research. What we can say is that for our problem, the effects of gravitation are so small that can be considered negligible. So the Coulomb interaction between the nuclei, or the Coulomb interactions between the nuclei and the electrons, and between the electrons, is much larger than the effect of gravitation. So gravitation can be totally neglected.
Thank you. If there is another question. Okay, we have another question by Nihad. Please introduce yourself and which level are you? Nihad, you can open your mic.
Hello, Dr. Fatma and everybody. My name is Nihad Omar, and I am assistant professor in Sudan University of Science and Technology, and I am a beginner in DFT. Now I know why you say that DFT is very hard because of all these equations and these things. First, I want to ask about Hamiltonian. What is Hamiltonian?
Hamiltonian.
Yes, what is Hamiltonian?
So, so what you said is that DFT is hard. DFT is a very simple way in order to approach the many body problem, or in order to, let us say, to yes, in order to approach is another easy way to approach the many body problem. But what is hard is to calculate the observable, okay? Because the wave function is very complicated, and this is what you will learn in DFT, okay? And so the Hamiltonian is the, let us say, okay, so in classical mechanics, you had a total energy of the system, let us say. If we take a harmonic oscillator, a simple way, okay? So if you have a particle, okay, that is moving under potential, and in this way, the potential is is the is this term here, okay? The potential also is related to the force, right? The force is a minus gradient of the potential, right? So in order, if we have a force, we can calculate the potential. And then if you want to calculate, if you want to write the total energy of the system, so is a moving of the kinetic energy of the particle, because the particle, let us say, is moving, plus a potential energy, which is this one. So this is what you have learned in classical mechanics, in the way to write the total energy. But in quantum mechanics, the way we write the total energy, the total energy, let us say, is by using operators, okay? So because the P and the X, let us say, that you know in classical mechanics are not the one you know in quantum mechanics. They are defined in a different way, okay? Then if we want to write, let us say, the Hamiltonian, okay, which is the correspondence of the total energy that you know in classical mechanics, but now we call it Hamiltonian, okay, in quantum mechanics. So it is the things that you use to define your system. So your system is, let us say, for harmonic oscillator, has a kinetic energy. In this way, you will write just the P as a P operator, okay? And the P operator in quantum mechanics is defined in this way, okay? And then you have another term here, which is the position. Then you write it in operator form. Then just the harmonic, the Hamiltonian of the system is defined in this way. And then from our interest, let us say, as I said, if we have a system of, let us say, that is have atoms, okay, in which we have electrons and then we have the nuclei, then the Hamiltonian in this way is defined in this way, okay, in which you count also that electrons are moving around, then you put the kinetic energy of electrons, nuclei are moving around, then you count for the kinetic energy of the nuclei, and then there is also interactions between them, between electrons, between nuclei, between electrons and nuclei, and you count for everything, and then you put it here, okay? And this is what we call the Hamiltonian.
Okay, thank you. Now I get the Hamiltonian, right? Also, I want to ask you, I plan to come back to this lecture and learn it deeply, but I noticed there is a lot of symbols here that has no definition.
Which symbols, for example, yeah? Which?
Mm-hmm. A lot, like here, V, T, in this slide. And
yeah,
you can see a lot of them in a lot of slides, like epsilon.
Yeah, so here we have T, like just for kinetic energy. You can call it also another thing, K, for example. Okay, this is just to define a kinetic energy. And then E is for electrons, just an N for the nuclei and these things. Maybe what is important is, for example, when you see I, here we have sum over I, gradient of I. It means that we are summing for each electrons, okay? So imagine that we have 2 electrons, then the kinetic energy for this will be minus h bar over 2 square over 2m, gradient 1 square plus gradient 2 square, because we have 2 electrons. So we have 1 and 2. And then, for example, here we have I capital, which we have the nuclei. So we do the interaction between electron 1 and nuclei 1, then electron 2 and nuclei 1, electron, and this thing, okay? And the same is also for the nuclei. Yeah.
I just say that it will be very helpful if we put the definition of each symbol in the.
Okay, I'm sorry. Yeah, I just yeah, and Z
Thank you.
of course is atomic number, and yeah, so yeah.
Okay, thank you a lot, Dr. Fatma, for this valuable presentation.
You're welcome. You're welcome.
Thank you so much, Fatima, for the lecture and also answering the question. Now we'll go to the second part of the lecture given by Professor Matteo Gatti. Please, Professor.
Okay, so anyway, I will be here till the end. Yeah, okay. I should.
Can you mute yourself, Professor?
Yes.
Unmute. We cannot hear you.
But Ala, do they want to
Salam alaikum.
break or something?
Can you hear me?
Wa alaikum assalam. We can hear you, yes.
No, I muted myself. Okay, maybe I do like this. Now it's okay. I think now it's okay. You do? You talk?
Okay. Yes, now can you hear me?
Yes, we can hear you.
Very good.
They can hear you?
And we can hear you also, Fatima.
Yes, now
I will look.
yeah, we are in the same room. I have the pleasure to work together with Fatima.
Do you want me to go to my office?
No, stay with us.
Okay.
And I have the pleasure to be with you this morning. So thank you very much for the kind invitation. And it's a pleasure to be with so many people from Sudan and I guess also from Palestine. So I hope one day I can come to Khartoum and also I can come to Palestine. But today we will be online. Please feel free to interrupt me whenever you want. So just open your mic. Don't hesitate to ask any question. I'm not sure I will able to answer all the questions, but there are no stupid questions, only stupid answers. Okay? So please do not hesitate. This is an opportunity for you. Don't be shy. There is no need to be shy. Okay? It's just a discussion that we are having all together. Is that okay? It's a deal for everyone?
Sounds perfect.
Okay. Now, do you see my presentation here?
Yes, we see it, but it's not in the presentation mode yet.
Yeah, I will just leave this like this because it's going to be short in this. But
Okay.
I would like to know if you can just remind me what date today is. Can you please?
27.
27 of
27 of July,
which year?
2026.
Thank you very much. This was actually a question also for the participants. If you don't ask questions, I will ask questions to you. Okay? It was just a test. Now, you see, this is a paper, and the author is E. Schrödinger. So now you should be familiar with this family name. Actually, Erwin Schrödinger is the father of the Schrödinger equation that Fatima has just introduced. And here you see an article from Physical Review. And if you just take a look at the first line, you would see that the date of this paper is December 1926. So this paper is actually 100 years old. It's a paper where Erwin Schrödinger has introduced the Schrödinger equation. So we are now discussing about an equation that is 100 years old. Exactly. This year we are celebrating the anniversary of this equation. Okay, so it's a very old problem. And why are we still dealing with this? Well, we can also take a look at another paper, and the author of this paper is Dirac, Paul Dirac. Schrödinger was German, And Paul Dirac is from UK. So he was working in Cambridge, as you see here in the affiliation. Dirac is another father of the fathers of quantum mechanics. Is the person who introduced spin in quantum mechanics and a Dirac equation that is a generalization of the Schrödinger equation. And he wrote an article in 1929 whose title is Quantum Mechanics of Many Electron Systems, which is actually the topic of interest for the school we are attending. And this problem was introduced by Fatema. And it's interesting to read what Paul Dirac wrote already in 1929, so just 3 years after the introduction of the Schrödinger equation. He writes that the general theory of quantum mechanics is now almost complete. In particular, the physical laws that are necessary to describe a large part of physics and entirely chemistry are known, and is referring to the fact that the Schrödinger equation is actually the equation that describes the interaction between the electrons and the nuclei. And if you are able to solve this equation, then you are able to describe the properties of molecules and materials. So already is saying that we know this equation. So in principle, we can describe the properties of molecules and materials. But then he immediately adds that difficulty of that now we are facing, and is referring to 1929, is the fact that these equations are too complicated to be to find a solution. And therefore is already claiming that we should look for an alternative to the solution of this many-body Schrödinger equation to find a solution. And he would like to have an alternative in such a way that we can indeed find, we can reach the goal that we would like to have reached, that is the description of complex materials without having too much calculation to be carried out. And this is indeed the program of the school that you are attending. The program will be the introduction of density functional theory. And density functional theory is a many-body theory of a collective variable that is the density. And it's one possible way of rewriting the quantum mechanics that Fatema and I are introducing today for the many electron system. And the reason why we have to find an alternative way, a way of rewriting quantum mechanics, is indeed what Paul Dirac is writing here. The direct solution of the many-body Schrödinger equation is too complicated, and actually we don't want to find this solution because the goal, as Fatema has already introduced, is actually to calculate observables. And observables are these integrals of this many electron wave function. And the idea is of DFT is to rewrite these expressions in terms of a simple quantity that is the electronic density. So starting from tomorrow, I guess, your agenda will be indeed how to rewrite the problem that Fatema and I are introducing today. But today we are going to discuss a bit more in detail the problem that we would like to solve together, that is this Schrödinger equation for the many electron system. Is this clear to everyone? Yes or no?
Yes.
That's an easy question. Yes?
Yeah, because clear.
Okay.
Yes, it is clear.
Very good. Then I will stop sharing here, and I will try to share in here. Okay, now you should see again my screen, and I will not use slides, but I will write, okay, as if it was a whiteboard. Now, You have to be careful because I'm very bad in writing. My handwriting is very, very bad. So if you are not able to read what I write, you should shout. Okay? Please stop me if there is something that you cannot read. I hope you can read what I wrote here. What did I write? Can you read?
Problem to
Problem
be
to be
solved.
To be
solved.
solved.
Very good. Then it's working. Okay. What is the problem that we want to solve? As Fatema has already introduced, it's the Schrödinger equation. And actually, which is 1926, okay? So 100 years old. There are two different kinds of problems. The first one is the problem that is called the time-dependent Schrödinger equation. It's this differential equation in terms of the derivative with respect to the time. So this is the derivative with respect to the time of the wave function psi of t. And this is the right-hand side. And on the left-hand side, we have the Hamiltonian h that is dependent on time t that is applied on the wave function psi of t. And the question that we ask in this case is, what is the time evolution of the system? And the system is described by this wave function psi of t. This is a typical question that we have when we apply, for example, when we are in a situation where we have a time-dependent electromagnetic field. Applied on a material or a molecule, and this can be, for example, a laser or some other electromagnetic field that is time dependent, and this is driving our system. So it's changing the properties of the system, and we want to understand the time evolution of the system. We want to calculate observables as a function of the time. So I indicate an observable with the letter O. This is the typical question that we want to answer when we consider the time-dependent Schrödinger equation. Now, if there is no time-dependent potential, Fatema has already shown you that the Schrödinger equation becomes a simpler equation that is an eigenvalue problem. So this is first order differential equation. If there is no time-dependent potential, then the Schrödinger equation becomes an eigenvalue problem. Where we have the Hamiltonian that now is time independent applied to the wave function psi, and this is equal to E, which is the energy, times the wave function psi. And the question that typically we want to answer in this case is, what is the ground state of the system described by the wave function psi? What is the ground state? It's the energy, it's identified by the energy E0, which is the minimum of all the possible energies E. And this corresponds to the expectation value of the Hamiltonian with respect to the wave function in the ground state that I call psi 0. Okay? So typically, in the context of the time independent Schrödinger equation,
Matteo, someone is raising his hand.
if someone is raising the hand, this person should immediately open the mic and ask the question. Thank you, Fatima. Please go ahead.
My question My question is, what is different between time-dependent Schrödinger equation and Heisenberg bit?
And Heisenberg? I missed the last word. Can you repeat? Heisenberg what?
Otaiba, can you ask your question again?
I just missed the last word.
Yeah, me too.
Otaiba, can you...
Heisenberg bit.
Heisenberg?
Heisenberg picture.
Picture.
Yeah.
Ah, okay. That's something more advanced. It's related to the fact that we can introduce what we are now describing is what is called the first quantization. You can also introduce the so-called second quantization, where you have a more general description in terms of field operators. So this is just more advanced. Okay, I will not introduce this. So I will avoid to answer the question because this will require something like another hour. Okay, it's possible to rewrite all the equations that I'm showing in a different formalism, where you introduce different field operators. We are not going to do this. Okay.
Maybe he will see when he starts to learn about TDDFT.
Okay, any other question? Otherwise, can I continue? So I was just saying that in the case of a time-independent Schrödinger equation that I've written here, it's an eigenvalue problem, and we are interested in finding the ground state that corresponds to the minimum energy of the system among the possible eigenvalues E that are the solution of the equation. And this is typically the problem that you will face in the following. And DFT is actually rewriting these equations. The time-independent Schrödinger equation. So we are going to focus on equation number 2, and we will not consider equation number 1 in the following. So we will assume that we are in a setting where the Hamiltonian is time independent. And our goal will be to find the ground state of the system. Why we are interested in the ground state? Well, because from the ground state of the system you can obtain different properties. For example, you can study the relative stability of different configurations of your system, which means different distribution of electronic charge. And this is, for example, in a material or in a molecule, if you change the geometry of the structure of the material, you want to know which is the structure of the material that is energetically favorable. So you want to calculate for each structure the energy of the corresponding structure by solving the Schrödinger equation. And then you want to understand which is the minimum of the different structures. And from the distribution of the electronic charge, you can understand, for example, the bonds. If you also consider the spin, you can have the magnetic moments. So the distribution of the spin of your molecule or your material. Okay, so this is in general what you want to solve. You want to find the ground state of your system. Now, in the Schrödinger equation, we have to specify which is the Hamiltonian. And the Hamiltonian was already introduced by Fatema, but let me write it again. because I will take a different convention with respect to Fatema, in the sense that I will use different symbols, so different notation with respect to Fatema. So the Hamiltonian is the Hamiltonian for the electrons, which means that we are considering a Born-Oppenheimer approximation. So we solve the electronic problem for fixed nuclei positions, and given the positions of the nuclei that are fixed, we are just solving the problem for the electrons. So the electronic problem depends parametrically on the nuclei positions. And the nuclear terms are just additive constants, and we will neglect them. Okay? They are not important for the determination of the electronic distribution. I will use... Yes?
Excuse me, what is the third term in the Hamiltonian equation?
I will now read all the terms, okay, so it will be clear soon.
Thank you.
Okay, so it's important to, first of all, realize that we are solving just the problem for the electrons using this Born-Oppenheimer approximation that Fatema has introduced. Okay, so the nuclei are fixed. We just are dealing with the electronic degrees of freedom. Then here I will use the so-called atomic units, which means that we will put the electronic charge E equal to h bar equal to the mass of the electrons to 1. Then for the notation of the different variables, I will use that x is equal to r and sigma, where r is the position of one electron and sigma is the spin of the electron. And in principle, r is a vector. I think Fatema was writing an arrow like this. I will not.
I remove it and I put it.
I will not write it with an arrow because otherwise it's going to be too complicated. And the other important observation is that our temperature is 0 K, and we are assuming that there are no relativistic correction. Which means that the Coulomb interaction is instantaneous, for example. There is no spin-orbit interaction. Okay. Of course, the instantaneous Coulomb interaction is violating relativity, where we know that the speed of light is finite, but this is considered as a correction with respect to what we are now dealing with. Okay. And there are no external fields. So as I said, our problem is static. It's the problem that Fatema has already introduced. Now let's go back to the Hamiltonian. The Hamiltonian has three terms. So the Hamiltonian is H. It's the sum of the kinetic energy T, the external potential Vx, and the Coulomb interaction W. The Coulomb interaction is the Coulomb interaction among the electrons. So let's write it again explicitly. It's the sum of three terms. The kinetic energy of the electrons is simply the sum from I1 to n, where n is the number of electrons, where I have minus the Laplacian, that is nabla I square divided by 2. Then we have the so-called external potential, that is the sum from I1 to n of an external potential Vx of Ri, and Vx of Ri is the interaction between the electron at position Ri and all the nuclei in the system. As Fatema, we indicate here the nuclei with the index capital I, and we assume that we have n80 nuclei. Each of them has Z number Zi, and the Coulomb interaction between the electron at position small ri and the nucleus at position capital R capital I is just given by the distance between the two. This is the Coulomb interaction. This is the interaction between the electron at position Ri and all the nuclei at positions capital R, capital I. And this is a Coulomb interaction. It depends on the distance between the two of them. And then we have the Coulomb interaction W, that is the interaction between the electrons. And this can be written in different ways. It can be written as 1/2 the sum I and j, where I is different from j, and the distance between Ri and Rj. Or it's also the same as the sum for I smaller than j of, again, the Coulomb interaction between the electron at position Ri and the electron at position Rj. So this is the Coulomb interaction between the electron at position Ri and the electron at position Rj. And I have to sum over all the pairs of electrons. Is this clear? This is defining the Hamiltonian, that is the one that we have in our Schrödinger equation, this one, that we want to solve. Is this clear? Is there any question? My question is easy. Again, you have simply to answer yes or no.
Hello, everyone.
This was already introduced by Fatema. Now I'm just using my notation and my bad way of handwriting. So it's important that you can read. Can you read?
Yes, I can.
Now, all this seems pretty easy. The equation to solve is here. We know everything. So in principle, it's just a matter of solving the equation. Now, why Dirac was complaining? What was the problem of Dirac. Why Dirac said this is too difficult to be solved? So why is this difficult? Besides being able to decipher my handwriting. Why is this difficult? Now, in the Hamiltonian, we have two kinds of potentials, of terms. We have the kinetic energy and the external potential that are so-called T and Vx are so-called one-body operators. Because if you look at their expression, they are just a simple sum over I. They depend, each of them depends just on the position of each electron separately. And the position of each electron is indicated by the index I. So they are called one-body operators. But then we have the Coulomb interaction W. In the following, I will not also indicate all the operators with the hat, just to simplify. Okay, so forgive me about this, otherwise it's going to be too long. So in the Hamiltonian, we have these one-body operators like T and Vx, but then we have the Coulomb interaction that is a two-body operator. It depends on the pair of electrons. You see, in the Coulomb interaction, it's the expression depends on the sum over I and j, and each term depends on I and j. While in the one-body terms, we have just a dependence on I. And this is the origin of the problem. It's the Coulomb interaction. It's the origin of the problem. The electronic degrees of freedom are coupled together.
So we can't factorize the
Which means that the many-body wave function, the wave function, cannot be factorized. It means that we cannot solve the Schrödinger equation for each electron I that goes from 1 to n separately. We can solve the Schrödinger equation only for all the electrons all together. Now, contrary to the example of the harmonic oscillator that was introduced by Fatema, n, the number of electrons, is not 1, but n is very large. In the case of an atom or a molecule, it can be number of tens, okay, some tens of electrons. In a solid, it's a number of Avogadro of electrons, so a huge number. So the problem is difficult for two reasons. One is that there is Coulomb interaction between the electrons, and number two, the number of electrons is very large. Okay, how can we see this problem concretely? So in the let's assume that we have just n equal 1, just one electron. Then the equation to be solved is this, okay? And the wave function is a function of position r. This is what Fatema has discussed. Now let's assume that we have just a system with 5 possible positions, 1, 2, 3, 4, and 5. Okay, so the size of the wave function is 5. Okay, we just assume that our space is made of 5 points. So the size of the wave function is just 5. Is this clear? Yes or no?
Yes, clear.
Okay, very good. Now, if this is clear, let's make the problem a bit more complicated. We assume that there are 2 electrons. Without interaction, we could say that we have the wave function for the electron 1, that I call psi1 of r, and then we have the wave function for the electron 2 that I call psi2 of r. Now each of them has a size 5. 5 for the first and 5 for the second. So the total size of the object that I need to describe in order to describe the system is 5 times 2. So it's 10. Okay? Do you agree? I have just doubled the problem. I have 2 electrons, each of them described by a wave function that I call psi1 and psi2.
Excuse me, can I ask a question?
Sure.
You mean by the first when n equals 1 that there's one electron that interact with 5 electrons?
No.
And
No,
then
no,
the
no, no,
second...
no. There is one electron only, and the space is made by 5 points. So the description of the system is given by the wave function psi of r, and r is the position of the electron, but the electron can only take 5 positions. Is this clear?
Okay. Only 5 possible positions for the electron?
Yes.
5?
Yes.
Yes, okay.
Mm-hmm.
Okay.
Now, do you agree that if we go to a system with 2 electrons without any interaction, we can assume that the first electron is described by the wave function psi1, and the second electron is described by the wave function psi2. And each of them can take only 5 positions. Okay? The total size of information, the total amount of information that I need to describe this situation is 5 times 2 equals 10. Is this okay? Yes or no?
Yes. I think... I think it is not
You think that?
Excuse me?
Yes, go ahead.
If N1 is in the first position, then side 2 has 5 possible position.
Yes.
Yes. And
So
then
each
we
of
have
them can take, each electron can take 5 different positions. So each object, each function, psi1 or psi2, can have 5 different positions. So the size of this object is 5 for each of them. I hope it's okay. If not, please tell me. Because now we go to the situation where there is interaction. And the interaction is the Coulomb interaction W. In this case, we cannot factorize the wave function in terms of the two single particle orbitals psi1 and psi2, but the object that is describing our system is a wave function that depends on R1, or let's call it R and R prime. Okay, it's a function of two coordinates. The coordinate of the first electron.
Excuse me?
Just 1 second. And the coordinate of the electron 2. Yes?
Can I ask about n equals 2? 5 by 2 is the combination of the two electron positions?
Yes.
You mean that?
Yes.
I thought it should be 25, not 10. If the electron is, because if the electron in position 1, there is 5 possible positions for the second electron.
Yeah, this is
not
indeed
working
what
like
I'm
this.
going to discuss now, because in the case we have just seen, these two are completely independent. Okay, so the electron number 1 can be anywhere, and the second electron can be anywhere. There is no correlation between the two. They are not coupled. They are simply independent. Okay? Each of them can take these 5 positions, but they are independent. Instead, if the electrons are interacting, then the wave function depends on the coordinate of the two electrons together, not separately. So it becomes a function of R and R prime together. And this object has indeed a dimension 25. Now I have to put 25 points, and that's why I decided just to have 5 positions. In this case, instead, the electrons are coupled and the wave function depends on 2 coordinates at the same time. This is different from the previous case, where the 2 functions were simply function of 1 coordinate. So in total, I had to give the value of the function at 5 different points. Each of them, 5 times 2 is 10. Now I have a wave function that depends on 2 coordinates at the same time, and therefore the size of this object is 25. And in general, this is different from the product of 2 wave functions. This is the general case in case there is interaction for 2 electrons. Now we can generalize to the case of n electrons. For the non-interacting case, let's write it here. I need n single particle orbitals, each of them describes the position of one electron. So I have psi 1r, psi n r, where the points are for psi 2r, psi 3r, and so on. Which means that in my case, with 5 positions, in total I would need 5 times n. This would be the amount of information I need in order to describe the configuration of the system with n electrons. In the interacting case, instead, I have a wave function that depends on R1, R2, Rn. Now, 25 is actually 5 squared. And this is different from the non-interacting case where I multiply 5 by 2. And in the general case, this object is growing exponentially with the number of electrons. And this can be huge. If n is large, and if we have a reasonable amount of positions, this object becomes a huge object. The scaling is, which is the growing of this object with the number of electrons, is exponential. In the non-interacting case, instead, this object is scaling linearly with the number of electrons. That's why the Schrödinger equation for n electrons is so difficult. It's because we cannot decouple the solution in terms of the orbitals for each of them describing a single electron. It's not possible, and this is due to the fact that there is this Coulomb interaction W. The origin of the problem is this Coulomb interaction W that is coupling the electronic coordinates. And since we have this interaction W, the wave function is an object that depends on all the coordinates of all the electrons from 1 to n all together. It cannot be separated in terms of the single particle orbitals. As a consequence, the scaling, so how the problem is growing with the dimension, with the number of electrons, is exponential. And this object, psi of R1, Rn, cannot be calculated and cannot be stored because this can be huge. That's why Dirac said that the problem is too difficult to be solved in a straightforward manner. Is this clear to everyone? Do you agree that this is a difficult problem?
Yes.
Yeah, it's so difficult.
And it's difficult for these two reasons. There is the Coulomb interaction between the electrons, and the number of electrons is large. Now, this is difficult, but it's the one that is paying my salary. So I'm very happy that it's difficult. And this is still an open problem, okay? So this was already discussed in 1929 by Paul Dirac, but we are still discussing the problem together, which means that there is no exact solution of the many electron problem. And the reason is that it's too difficult to be solved. Now, I guess we will conclude this discussion by saying that actually we don't want to solve this problem, okay? And this is what DFT is about. But now maybe we would like also to discuss why we want to do it. So why is this problem useful? And why is interesting? I will just briefly say why this is useful, because you have a lecture on this topic, which is the topic of computational materials design. What I mean is that if you are able to solve in some way or another this complicated many electron problem, you can design or discover new materials. You can predict properties of the materials that can be then also realized experimentally. You can guide the realization and identification of materials. You can study their properties. You can work with the experimentalists that are doing the real experiment on the real samples. So this is a very powerful tool for today's materials science, for physics, chemistry, biology, even astrophysics. There are many different applications of the solution of this many electron problem. So this is nowadays a central problem for many different applications. You can use this to discover new materials for energy applications, for example, for renewable energy, for catalysis, many different applications. You can also use this to study materials of our cultural heritage. The number of applications is more or less endless. And there will be a lecture just about this. And this is actually the main reason why people are studying DFT, because they want to use this theory, this approach for useful applications. I want just to make a remark here. It's the fact that nowadays we are living in the age of artificial intelligence, which means that the computer is nowadays even able to write itself independently, alone, an input file for a software that you will learn to use. So nowadays it's not so crucial to be able to write an input file, because you can ask ChatGPT or Claude or any artificial intelligence that you prefer, that you find online, to write an input file for Quantum Espresso for you. So that's important, but it's not crucial. The crucial point is to understand the result of the calculation, to be able to interpret what you are obtaining, to understand whether the result of your calculation is correct or wrong. So it's important to learn the theory, and it's even more important than in the past, because the computer is stupid, but you are smart. So you have to guide the computer to find the good answer to the questions that you have. Don't rely just on the computer. The computer is stupid. You are the smart person. Use your brain. Your brain cannot be replaced by a computer, okay? But in order to use your brain, you need to learn the theory. You need to learn the equations. You need to learn why we are doing what we are doing, okay? What your approach is supposed to give you as an answer, and what your approach is not supposed to give you as an answer. And we already mentioned an example at the very beginning. We said that DFT is about the time-independent Schrödinger equation. So it's about finding the ground state of the system. If you are instead interested in the time evolution of the system, where you have to solve a Schrödinger equation that is time-dependent, then you cannot use DFT. And the computer doesn't know this. You know it, okay? So you have to guide the computer to find the answer to the question that you have. But the questions come from you. Okay, so be careful about this. It's critical that you know what you are doing. The computer is not able to tell what the computer is doing. Is this clear? That's why we insist so much on the theory. Fatema has a comment. I think you should come next.
I can ask you, just, I think that we hear.
Can you
So
hear
you said-
Fatema? Sorry.
You say
No, we cannot hear you well, Fatima.
Fatima,
So-
just come here.
you can repeat my question.
It's
Yeah.
easier.
So you were saying that the many-body problem is complicated but interesting, and then so yes, so we that is why so I was mixing one word. So we use alternative theories, okay, that give us the same thing that we can obtain. But do you think that because you have mentioned many interesting things that why this problem is still interested and these things.
I just
But do you
mentioned
think
why it's
that-
useful. I didn't say why it's interesting so far.
So yeah,
Uh-huh.
you mentioned why it's useful.
Mm-hmm.
But do you think when we use so it's useful? Okay, so because we use also alternatives, is useful because you are talking about why we bring up alternative theory, or because like if we go in the way that we have to go, like by using the wave function and try to solve the problem and these things, and we bring out alternative theory, do you think we miss up something? You get it?
Yes. So Fatima, I don't know if you could understand what Fatima is saying. Fatima is saying, okay, the many-body Schrödinger equation is useful because I mentioned different applications. But then I'm already discussing the fact that this problem is too difficult to be solved. And so in your agenda of these 2 weeks, you will have to find an alternative strategy. And now Fatima is asking whether we are going to miss something developing these alternative strategies. And the answer is, in principle, no. In practice, yes. But this is something that you will see in the following. So I cannot anticipate too much. Okay?
Okay, yeah.
Mm-hmm.
But all the useful things that you have mentioned can be done in the two way.
In principle, all the observables that are expectation values of operators with respect to the many-body wave function can be rewritten in principle exactly in density functional theory as functionals of the density. In principle, we can obtain the same answers as in quantum mechanics. In practice, it's not so straightforward. But since you don't know yet DFT, I cannot comment too much on this.
Okay, so we will learn, yes.
Okay, thank you for the question. Now, I would like also to say not only why this is useful in practice, but also why this is interesting from the conceptual point of view, from the philosophical point of view. It's because the many-body, the many-electron problem is probably one of the most prominent paradigm of complexity. What is complexity? Complexity can be defined in terms of the properties of a complex system. One important property is the so-called emergence. It's the fact that the wall is more than the sum of its parts. So if you have a system of electrons, like the one that I'm drawing, each of the points is one electron. All these electrons are actually interacting. And now I'm just drawing these interactions. Maybe let me redo it just to be more clear. Change the color. These are the interactions. All of them are interacting. Okay, I'm just drawing some of them. The effect of the interaction is the fact that the total system is behaving differently from just the sum of the independent parts. And the point is that we have to focus on the interaction. The interaction, in particular the Coulomb interaction, is what is making the problem interesting. There is a very simple example. It's the fact that you have a molecule of water, H2O. This is different from just having two separate atoms of hydrogen and one atom of oxygen. Okay? A molecule of water has properties that are different from the sum of the properties of its constituents. And this can be generalized to a system with many number of electrons. Okay, so this is an important property of a complex system. Another one is that the electrons can have a collective behavior, which means they can do all together the same thing. They can respond collectively to a perturbation. And this is in contrast to their individualistic behavior, which is the result of the fact that the electrons want to stay far apart from the others, and it's related to the Pauli exclusion principle as well. So there is a competition between these two different behaviors, and collective behaviors are, for example, the creation of particles like plasmons or magnons. Plasmons are the collective oscillation of a charge of the electrons, and the magnons are the collective oscillation of the spin. They respond all together to some external perturbation in a collective way. Other examples of collective behaviors are phase transitions. For example, metal to insulator transition. The electrons are all together changing macroscopically the property of a material. Another characteristic is the fact that complex systems are sensitive, very sensitive, to external control parameters like temperature, pressure, external field, and so on. So you can change the temperature of the system, you can apply a pressure, and the properties of the system are changing dramatically. And all of this is also reflected in the huge variety of molecules and materials. In contrast to other areas of physics and chemistry, the equation to be solved is known. We have written it. We know all the terms in the Hamiltonian. We know the equation to solve. In other areas of physics, we don't know the Hamiltonian. We have to make approximations. Here we know the Hamiltonian, and still we can find many different solutions of this Hamiltonian that correspond to the different realizations of molecules and materials. So all this is actually super interesting. It's amazing that we can find all this variety of molecules, materials, and their properties. And these properties are very sensitive to small changes of the general parameters that are controlling the system. The electrons can respond collectively. All these are questions that per se are super interesting to study. So even if you are not interested in concrete applications of this problem, all this is super interesting from the intellectual point of view because it's a prime example of complexity. And this can be applied to other areas of science and more even wider than science, even in sociology and other contexts. It's very interesting to study complex systems.
I have another question.
Yes, Fatema has a question, but you have to come here because otherwise they don't hear you.
Yeah, so many of the properties that you have mentioned can be obtained by solving the Schrödinger equation, obtaining the wave function, calculating observable, or some of the properties can be also obtained by adding another term to the Hamiltonian, like external potential, in order to find out some properties, right?
Yes.
So, yeah, this is the question.
Yes, I hope you understood the question. So Fatema is saying that if you apply an external field, an external perturbation, then you maybe have to add a potential to your Hamiltonian. Yes, the answer is yes.
Yeah, and
is there any other question from the audience? Is there any other question?
For example,
are you still with us? Yes or no?
Yes, we are.
Yes.
Okay.
We are here.
Very good.
Hi,
Do you have any question?
I do have a question, Professor.
Yes, please.
How are you? Thank you very much for the nice introduction or nice lecture about like deep physics of the DFT. I'm actually like started to study DFT and its application on computational material science like maybe a year ago or something, or a year and a half.
Sorry to interrupt you, Mason. Can you introduce yourself, please?
I'm a PhD student in University of Sharjah, American University of Sharjah, pursuing my PhD. So I'm kind of independently working on this. My professor, he is new to this round. He's a very good theoretical physicist, but like we're starting this line of computational recently. So I've been studying this theory, and now I'm in the practical part of applying this through quantum espresso, and now I'm learning VASP. But like you have said something interesting a bit ago, like you've said that learning this theoretical background is useful as much as it's interesting as well. But you've said something like really catch my attention, that you said of course, we can use AI to produce those input file and stuff. They can help us also debugging what the problem with the calculation if there is an error or so. But you have said something about like learning the theory can help us verify our like final result or so, or like it can let us judge at least the result that we obtained from those calculations. So I would be happy to learn from you how we can sometimes verify those results, because it's like it's a quantification thing, and all these equation is kind of like, for me it's rigid theory, or we cannot solve it by hand, right? This is what you also like emphasized earlier, that those like solving those problems, or those Schrödinger equation for many body problem, it's kind of complicated or hard to be solved like by hand or mathematically, right? So we use computers to do so. But I couldn't find the connection between how can we verify the result that we collect from those programs, either quantum espresso or VASP or whatever used for DFT, and the result we actually like, the right results that we should like expect.
Yes.
If you can maybe comment on that, or
Yes,
I'm not sure if my
this,
question
I
is
think,
clear.
is a crucial point for you in these 2 weeks. I think that nowadays the goal has been shifted from learning only how to run a code, which can be done very quickly nowadays, thanks to the fact that computers are available everywhere and softwares like Quantum Espresso are available everywhere. And you can have, for example, help from artificial intelligence to use these codes. And actually, all the properties of materials that are basic properties have been already calculated more than once independently by computers. So if you want to have a band structure of a material that for which the crystallographic coordinates are known, you don't need to run the calculation again. You find the results already available in different databases, which means that nowadays it's not anymore a matter of research to produce, for example, a Kohn-Sham band structure of a material. This has been done already several times by computers. So this is not your goal. Your goal nowadays, I think that's my my opinion, is the fact that we have to be, as researchers, able to formulate clearly the questions that we want to solve, that we want to address, and we need to identify which are the computational approaches that are suitable to give the answer that we are looking for. So I have not introduced DFT so far. I have just introduced the many-body Schrödinger equation that was already known in 1929, where Dirac was commenting about this. And between 1929 and nowadays, different approaches have been developed. You will be studying density functional theory. DFT is a way, as I said, of rewriting the many-body Schrödinger equation, in particular for the time-independent Schrödinger equation. And the question that you want to address in this case is, what is the ground state energy of my system? And DFT is supposed to give me the answer to this question. You will study this. But for example, DFT is not able in practice to give me the excitation energies of a system. It's not able to give me whether a system, by solving the Kohn-Sham equation that you will study, if a system is metallic or insulating. So these are the kind, in meaning that you cannot use the Kohn-Sham gap to see whether a material is metallic or insulating, because even the exact Kohn-Sham gap is not the real gap of a material. Now I'm already giving you concrete examples and I'm already anticipating what you will learn. My point is that I'm inviting you to learn the theory, to learn what the computational approach is supposed to give you, and to understand that if you do DFT, if you want to use DFT, this is one among different choices. So the strategy is to study the equations, to understand what is the meaning of the equations that you are going to solve, because you need to know what are the answers that you are supposed to find by solving these equations. And in practice, not all the answers are possible. Okay? So my invitation is just to study. Once you study the equations and you understand what you are doing, then you can also interpret the results that you are obtaining. After all, we are always making approximations and we have to know what we are doing. So it's plain invitation to study. Study the theory, not just focus on how to run a calculation with the software.
So yeah, I think Mason is doing calculation in the how to say, okay, in the ground state level, in the DFT level, and then I think her question is that how she connects the things that the results that she obtained.
Sorry, Fatima, we don't hear you well. Can you?
Yes.
You
okay.
have to speak up.
I have to talk loudly. What I am saying is that I think Maysoon, yeah, because we have a common friend and Mara, so she's telling me what she's doing and these things. And then I think she is doing calculation in the ground state level. And then I think her question is that how does can she connect the results that she obtained? I think, for example, she usually studies the stability of the system, stacking of the layers, band structure, things like this. How can she connect the results that she get out of her calculation to what she learned from the theory to know that she is doing things correctly, for example?
Yeah, that's a crucial question, but I cannot answer this question now because you should ask this question to the people that are introducing DFT and the approximations.
Yeah.
We are not introducing DFT
so,
yet.
Yeah, the idea is that you understand DFT, the theory,
yes. But my point is that you have to study DFT, the theory, if you are using DFT to run calculations. Don't run calculations without knowing what you are doing. Yeah. It's very simple to get to the wrong solution. It's like when you drive a car or you drive a motorbike. You can go very easily to hit a wall. You don't want to do this, no? If you go too fast, you're going to crash into a wall. But if you know how to drive a car, then you will be careful and you would avoid the wall. My point is, spend time in learning the theory. There is another question, please.
Thank you, Professor. Thank you, Fatima.
You're welcome.
We have another question from Nihad Omar. Please, Nihad, you can unmute yourself.
Hello.
Yes.
Thank you, Professor Matteo, for this rich lecture. I want to ask you about the importance of ground state system. You mentioned earlier that to calculate the minimum energy, and you mentioned that it is important to get the relative stability of different combinations.
Yes.
I want you to elaborate more in this area, and if it can be used to another things.
So, in general, we are interested in the ground state of a system at zero temperature because this is the situation, the configuration where an electronic system is if we don't apply any perturbation. Okay? So typically, a system wants to minimize its total energy and therefore it stays in the ground state, which is the state that has the minimum of energy. And we do calculations at 0 temperature because the electronic configurations, the different electronic configurations have an energy difference that is much larger than the temperature. Room temperature corresponds to an excitation energy that is much smaller than the typical energy differences between different electronic configurations. That's why we want to study the ground state. Now, typically, we want to compare different structures of a solid or different geometry of a molecule in such a way that we can understand which is the minimum of all the possible structures of a material or a molecule. We want to compare different crystals to know, for example, the crystal structure of a material. And this is a typical question that is related to the ground state. We want to know how the lattice parameters change as a function of pressure. For example, these are the typical applications we are interested in when we study the ground state of a system. And these are very important questions.
Thank you, Professor.
Okay.
There is also one question in the chat. Abu Adam is asking, explain how the total molecular wave function is separated into electronic and nuclear wave function.
This is a question for Fatema. So maybe we come back to this at the end. There is a question about the separation between the nuclear and the electronic wave functions. Okay. So this is related to the Oppenheimer approximation, and this is actually what you mentioned earlier. Yes. So I suggest that we switch back to Fatema at the end. Okay?
Okay. Okay. There is also another question in the chat by Sahar, but we can take these questions at the end.
Okay.
If you prefer, Professor.
Okay. Then let me continue. We were supposed to have a pause, but we are just
I think maybe after
going through it.
Then we can have at some point the pause, no?
Yeah, but then we are going to finish in 40 minutes. Huh? At noon, we are going to finish.
In 40 minutes?
Yes.
You are not tired? You want to continue? And ask them also if they are okay. If they
Can
are
you
not
hear Fatema or not?
Very far. Very far.
Fatema can't hear.
I am asking him if he is not tired, if he want to take a pause, and if you also people online, you are not tired, you want to take a pause. So you have another. You have to go.
We can continue. Depends on you, or we can make a pause. I'm just saying that we are now we are finishing in 40 minutes. So most of the time has already gone.
Yes.
So it's up to you. Do you want to have a pause?
You are muted, Ala. Ala, unmute yourself.
But we can take longer, no?
That's the question.
Sorry. I was suggesting we can take a break for 10 minutes and then we come back.
And
then let me spend 5 minutes on this and then we take a pause.
Okay.
And then before we continue, I have a question. So, Ala,
yes.
I mean, are you like, can we, if we don't finish what Matteo has, can we stay longer or you have to finish at 1?
No, at noon.
At noon? 12?
Yes.
At 12, yes.
Yes, at noon. Yes, at 12.
We can't stay longer if he didn't finish.
I will not
if he did not finish, we can stay longer.
Okay, she said we can stay longer.
No, but I have material for 30 hours. We are not going to continue for 40 hours. I will stop. Don't worry. I would like to make a comment on the different strategies to solve the many electron problem, and then we make a pause. Okay?
Okay.
So I will just make a list on different strategies to solve the problem. So the first strategy is to evaluate the expectation value of the Hamiltonian that is giving us the energy the best you can. And this is the strategy that is followed by quantum Monte Carlo, and nowadays neural networks in AI. Okay, it means that you calculate a huge integral in the best way you can, and the best way is by using stochastic methods like in quantum Monte Carlo, or you make use of neural networks that are in AI. This is strategy number one. You try to do these calculations by using a brute force method like quantum Monte Carlo, so you try to calculate explicitly these integrals. This is the most accurate way, but it's also the most expensive. It is able to produce benchmarks, but it's limited, so you cannot study complex system, no complicated materials. You can study nowadays, I don't know, bulk silicon, but you cannot study a system that has 100 atoms in the unit cell with these approaches. The second strategy is to approximate the Hamiltonian. So instead of using the original Hamiltonian, you use a model Hamiltonian. And in particular, you change the interaction. Examples are the Hubbard Hamiltonian, where instead of the Coulomb interaction, you change the interaction from the Coulomb interaction that depends on the distance between the electrons until the electrons have an infinite distance. It's always 0 to a on-site Hubbard interaction that it's called U. Now, not important to know all the details. The important message that you should capture here is the fact that in this approach, in this strategy, you replace the Hamiltonian with a different one. You change the problem. You introduce a model Hamiltonian, and the model Hamiltonian depends on parameters. You simplify the problem. The price you pay is that now the Hamiltonian depends on parameters that are not known. And then the problem is how you connect the model Hamiltonian with the real one. But there are people that instead of studying the original many-body Hamiltonian, they study all their life these model Hamiltonians, because there is interesting physics out of these model Hamiltonians. The problem is that these model Hamiltonians do not correspond to the original problem, and then you don't know in all cases how to connect the model Hamiltonian and the original one. Strategy number 3, you approximate the many-body wave function. Instead of the full many-body wave function, you consider an ansatz for the many-body wave function. and you try to improve the solution. This is a strategy that is used very much in quantum chemistry for small molecules. And the paradigm of this is the Hartree-Fock approximation. And then we have strategy number 4, which is avoid the problem. If the problem is too complicated, a possible way out is to avoid the problem. Right?
The easy way.
Yes. And it means that now you need to rewrite the problem. And this is what DFT does. And also Green's function theory or reduced density matrix functional theory. All of them are actually rewriting the quantum mechanics problem that we have just formulated. And you will study DFT, that is the first example of this rewriting of quantum mechanics. Okay? This is the agenda for the coming 2 weeks for you. Rewriting the problem. Avoiding the direct solution of the quantum many electron problem with the Schrödinger equation that we have just discussed together, and formulate this problem in a different way. This will be your goal with DFT. And from the fact that there are other strategies, you already see that's not the only way to go. It's one among possible ways. Is this clear? Yes? Then
Yes.
you deserve a pause. We see each other in 5 minutes, okay?
Okay, thank you, Professor.
Very good. So see you in 5 minutes.
مشتاقين بس زي ما اتكلمت معاك الأمور
So how's it going? Good.
Okay, we are ready to restart if you wish.
Yes, we can start now.
Okay, so the last important concept that we have to introduce is the fact that we are dealing with the set of identical particles. We have n electrons and they are the same. And in quantum mechanics, identical particles cannot be distinguished. That's an additional postulate of quantum mechanics with respect to the basic quantum mechanics for one particle that Fatema has discussed. What is the consequence of this? So let's consider observables. That, as Fatema has already introduced, these are measurable quantities. In practice, they are expectation values of operators, right? For example, we have the observable O, that is the expectation value of the operator O with respect to the many-body wave function psi. Now, the consequence of the fact that the identical particles cannot be distinguished is the fact that the value of this expectation value should not change for an interchange of the coordinates of these identical particles. What I mean with this? So the calculation of an expectation value is just a calculation of the observable with respect to the operator O, and in practice this means this is an integral for me, okay? It's an integral dx1 dxn if I have n electrons of the many-body wave function psi star x1 xj xk xn, the operator, and the same wave function x1 xj xk xn. Now this has to be the same as the integral of dx1 dxn, the wave function xi, and I can interchange the coordinates of j and k, for example. And the result should be the same. And this is for any j and k. So I can take any permutation of coordinates of the wave function. So the arguments of psi and the expectation value is the same. Now, any permutation, a given permutation, can be written as a combination of interchanges of two coordinates that is called a transposition. And an example is here. I have interchanged the coordinates j and k, and this is what I call a transposition. And I call it PJK. I interchange a pair of coordinates, the coordinates j and k. And the fact that I have to obtain the same result in quantum mechanics implies that the transposition PJK and the identified by this operator and the observable identified by the operator O are such that the two operators commute. And this is for any j and k and for any operator O. In particular, this has to be the case if the operator O is the Hamiltonian. So the Hamiltonian and the transposition operator commute. As a result, if two operators commute, there is a set of eigenvectors of the two that are in common. So the eigenvectors of the Hamiltonian H are also eigenvectors of the transposition operator pjk. This is a law of quantum mechanics. If two operators commute, then there is a set of eigenvectors of the first operator that is also that are also eigenvectors of the second operator. Now, which are the eigenvectors of the transposition operator? There are two kinds of eigenvectors that are relevant for us. Those that are symmetric, so those that are such that if you apply the operator pjk to the wave function, you get an eigenvalue plus 1 times the wave function. And then you have the anti-symmetric eigenvectors that are such that if you apply the transposition operator, you get an eigenvalues minus 1 times the wave function. And those that are symmetric are describing bosons, and those that are antisymmetric are describing fermions. And you distinguish the two kinds of particles just by the property of the application of this transposition operator to the many electron or to the many particle wave function. So the electrons are fermions. And there are other bosons that we are not going to study. So we are just studying the case of antisymmetric wave functions. Those that are the eigenvectors of the transposition operator with eigenvalue minus 1. Now, a generic permutation P, that is the case where I change more than one pair, when I switch more than one pair of coordinates. So a permutation of coordinates, which means the arguments of the wave function psi, can be always written as a combination of these permutation of these transpositions. Okay, permutation can be always written by combining a transposition that is change of a pair of indices. And the eigenvectors of the permutation are again the symmetric ones, and these are bosons, or the antisymmetric, and these are fermions. Now, the eigenvalues of the antisymmetric wave function psi a, that are those that are describing fermions, is given by the signum of P. So here it's SGN of P, and the signum of P is minus 1 or plus 1, and it is minus 1 if there is if the permutation P is given by an odd number of transpositions, and it's plus 1 if there is an even number of transpositions that is leading to the permutation P. And for us, that we are interested in electrons that are fermions, the many body wave function belongs to the antisymmetric set of the Hilbert space. Okay, those for which if you change two coordinates, then you get a minus sign. This is an important property of the many electron wave function that has to be fulfilled. Is this clear? Is this something that you have already seen in the past?
Yes.
Okay.
Yes, it is.
This is an important postulate that is completing quantum mechanics, and it's important for the many electron case. Okay. Now I would like to conclude our discussion with an important case, which is the case where we actually are able to write down the solution of the Schrödinger equation. And this is the case of a Slater determinant. So we wrote that the Hamiltonian is the sum of the kinetic energy plus the external potential plus the Coulomb interaction W. Now, in the case that the electrons are non-interacting, which means that the Coulomb interaction is 0, then the Schrödinger equation can be solved exactly. The Hamiltonian is in this case a sum from 1 to n of a single particle terms. So sum of one body operators, which are the kinetic energy and external potential. And then the problem can be decoupled, and you can solve the problem for each electron separately. And psi I is a function of r, only one coordinate. Instead, the original many body wave function, I remind you, is a function of n coordinates. And this is a single particle problem. Which means that you can solve this, and then you have a set of eigenvalues like the one that Fatema has introduced in the case of the harmonic oscillator. Okay? And you can order them according to their energy. So this is for increasing energy. So you solve n times single particle problem. For the orbital psi I of r. And then the total energy is given by the sum from 1 to n of the eigenvalues, epsilon I. And you can do this exercise for the case of two electrons. So assume that you have two electrons, there is no interaction. Then you can solve the problem and you demonstrate that the total energy is equal to the sum of epsilon 1 plus epsilon 2, where you have each of them to be the eigenvalue of a single particle problem. This is an exercise that you can do. Now, this is for the total energy. What about the wave function? So, we have to solve this problem in the case of W equal to 0, so without interaction. The energy is simply given by the sum of the eigenvalues epsilon I for the single particle problem. What about the many body wave function? Well, in this case, we know explicitly the solution, the many body wave function, that in general I write also with the spin in terms of the coordinate x1, xn. X is r and sigma. Is actually taking an explicit form that I indicate with the letter phi, and phi is called as later determinant. How do I write explicitly as later determinant? For the n electron case, it's given by 1 divided the square root of n factorial, where n is the number of electrons, times a determinant that I indicate with the vertical bar of the single particle orbitals, written in this way. So in the first row, I have psi 1 of x1 until psi 1 of xn. In the second row, I have psi 2 of x1 until psi 2 of xn. And in the last row, that is the row number n, I have psi n of x1 until psi n of xn. And then I have to calculate the determinant of this. In the case n equal to, this is 1 divided the square root of 2, psi 1 x1, psi 1 x2, psi 2 x1, psi 2 x2. And the determinant is, in this specific case, psi 1 x1, psi 2 x2, minus psi 1 x2, psi 2 x1. And in the general case with n orbitals, I have to take all the possible permutations and I have to calculate the determinant. I just gave here the explicit expression for the case n equal to. This case with n electrons is just more complicated because we have to calculate the determinant. It's a matrix of dimension n times n. In the case of n equal to, we know how to calculate explicitly the determinant. So it means that in the case there is no interaction, we can actually solve the problem. We can calculate the total energy and we can calculate the many body wave function. The total energy is the sum of the single particle energies that are the solution of the single particle problems, and the many body wave function as an explicit expression that is called as later determinant, that is built in terms of the single particle orbitals that are the eigenvectors of the single particle problem that I have written here. which means that in this case, without Coulomb interaction, I can actually decouple the problem of n electrons in terms of n problems of one electron, and I can solve the problem exactly in principle. So that's why I was saying at the beginning that the Coulomb interaction is actually paying my salary, because without Coulomb interaction we would be able to solve the problem. Okay, so we are in a situation where we are actually able to solve the problem exactly, but this is only because we are in a situation where the electrons are non-interacting. Now let me take again this later determinant, unless there are questions. While I rewrite this later determinant, let me know if there are questions. Is this clear? Yes or no?
Yes.
Did you already see this later determinant in your life, or it's the first time?
For me, it is the first time.
That's good. You are learning something. Otherwise, all this would be very boring. What about the others?
I see it before.
Okay. So for you, it's a bit more boring, but we can discuss it together.
No, it's not.
Okay, okay. So let's discuss this expression more in detail. Okay, this seems to be a bit abstract. Why we write this in this way? First of all, it's a matrix. Okay, let's look at the columns of this matrix. So we go from psi1 x1 until psi1 of xn. So if we go through the columns, we have the different particles that are at positions x and spin x1 until xn. So with the columns, we identify the different electrons. If we change the rows, so we go from psi1 to psi2, so on, this is given by the complete set of orbitals that I indicate with psi I of x, that are the solution of the one electron problem. That I indicate in this way. Now, if I interchange two columns of a matrix, the determinant of the matrix changes sign, which means that here, if I interchanging two columns, corresponds to the fact that I'm interchanging two particles. And if I interchange two particles, this later determinant, which is the many body wave function for the non-interacting problem, is changing sign, which means that this later determinant x1 xn is anti-symmetric wave function. By construction, this later determinant is respecting this property of the antisymmetry of the many electron wave function. Now, another property of the determinant of the matrix is that if two rows are the same, then what is the value of the determinant? Can you tell me? The determinant of the matrix that has two rows that are the same.
0.
Very good. The determinant is 0, which means that if the orbital psi I is equal to the orbital psi j, so the same orbital is occupied twice, then the oscillator determinant is 0. And this corresponds to the Pauli exclusion principle, which is a fundamental principle of quantum mechanics. It means, in practice, that you cannot put two fermions in the same orbital. The same applies if you have two electrons with the same spin that are occupying the same position. So if Ri is equal to Rj, this would imply that we have two columns that are again identical. And also in this case, this later determinant would be 0. Okay? So this later determinant is just a construction that is automatically respecting the antisymmetry properties of the many electron wave function. In particular, it's automatically encoding the Pauli exclusion principle. So that's a very important property. The later determinant, it is phi, is the solution of the many electron problem without interaction. It can be written in terms of single particle orbitals. And it's anti-symmetric. And the last important property of this later determinant is that psi in general is not the solution of the many electron problem. That's psi. So we have H psi equal E psi, where H is the interacting problem. This later determinant phi is the solution of only of the non-interacting problem. So in general, phi is different from psi. Phi x1 xn is different from psi x1 xn. But psi is actually forming a complete set of the Hilbert space of the many electron wave functions. Which means it can be used as a basis to represent the many body wave function psi. And in general, if you want to calculate an expectation value of an operator on the many body wave function, you can represent it as a linear combination of expectation values with respect to the oscillator determinant. And there are rules to calculate these expectation values. So this is very important. Is this clear? Is there any question?
What are the rules to calculate the
If there is any questions, please ask if you have.
So Fatema is asking a question, but no one is listening, so you have to come here.
But you listen, you can say it. It's not long.
So Fatema is asking which are the rules. And I'm not giving the rules, so
Thank you.
you should study. No, I can say which are the rules, but it's something that I'm not going to use, okay?
Okay, yeah.
So we can consider two classes of operators. That are those that are giving us the Hamiltonian. The first one is the sum of one particle operators, like the kinetic energy or the external potential. And I call this operator G1. It has this form. G1 is equal to the sum I from 1 to n of h that depends on Ri. Then I can calculate the expectation value of G1 on the oscillator determinant, and the result is that this is equal to the sum from 1 to n of the operator small h on the single particle orbitals psi I.
Yes.
Second is the sum of two particle operators. This is like T and Vx. And this is...
And there is I also somewhere in the H, right?
No. The H is always the same.
position of the...
It depends on the coordinate Ri.
Yes, depends on the coordinate Ri.
Yes.
Yes.
But the operator is always the same.
Okay.
So the second kind is like W, and I call this G2, that is 1/2 sum I j, I different from j, Ri minus Rj. And then you can calculate this explicitly, and the result is the following. It's 1/2 sum over I and j from 1 to n of this expression psi I psi j R1 minus R2 psi I psi j minus psi I psi j R1 minus R2 psi j psi I. These are called Slater-Condon rules for the operators like G1 and the operators like G2 that are one particle and two particle operators. In the case of the one particle operator, this is something, the result is something that is expected, if you want. In the case of two particle operators, you have sum of two terms. One is a direct term, and the second one with the sign minus, it's called an exchange term.
My point, why you are mentioning rules and these things come out naturally of the calculation?
This has to be demonstrated. So
Okay.
Fatema is asking why I call these rules, and this is because this is very general. It's the result of the expectation value of any operator that is one sum of one particle operators and two particle operators. The expression is always the same.
Okay, yeah.
And this is very important if you want to calculate expectation values with respect to many electron wave functions, because you can use these rules in terms of Slater determinants.
Okay.
So this is very important. But okay, this is already more than what I wanted to say. Is there any other question? Yes or no? If there is no question, then I leave you with a question. I think it's a fair deal. So Fatema said that if you take the square modulus of the wave function, this is giving the probability density of finding the electron at position R, and we call this n of R. So this is the density, and the electronic density is the key variable of density functional theory. Now, what is the operator such that the density is the expectation value of this operator? So what is the operator n of R such that if you apply n of R to the wave function, you get the density n of R? We have here the solution in terms of the expectation value. So I want to write n of R equal to an integral with respect to the wave function, an operator, and the wave function. And I want to know what is the operator O and what I have to put into the integral. And the result of this, since it's late, I immediately give you the answer, is simply this. Oops. So it's the integral dr1 psi star r1 delta, this is delta function, delta r minus r1 psi star r1. The result of this is simply dr1 delta r minus r1 psi r1 square. And you know that if you do an integral with the delta function, this is actually simply this. So we have seen that in the case of one electron, the operator for the density is simply R minus R1 as an argument of the delta function delta. Now, in the case of n electrons, the density becomes sum 1 to n delta function R minus Ri. So this is the density operator for the n electron case. And then, and this is the exercise for you, you can demonstrate that if you apply the density operator with respect to the many-body wave function, and the definition of the density operator is here, you obtain this expression. It's an integral, it's n times the integral dr2 until drn of the wave function psi star r2 until rn, psi r2 rn. And this can be also written as integral dr2 drn square modulus r2 rn. This is an exercise for you, and you see that the density, which will be the key variable of DFT, is actually a collective variable of many electron system. It's telling you the probability of finding one out of n electrons at position R. So this is not a single particle property. It depends on all the coordinates of the n electron system. Exercise for you. If you want, you can try to derive this expression. Let's put it in red. Okay, so I leave you with an exercise. Do you have questions?
Thank you so much, Professor. Now we can take some question. If you have a question, you can unmute yourself and ask your question. We also have some question in the chat. We said we will go back to.
There was a pending question for Fatema on the Born-Oppenheimer approximation. We will come, I suggest we come back to this at last, such way that you can share again your screen.
Okay.
Is there any other question? Be careful if you don't ask questions. I will add more exercises for you. It means that everything is clear.
There is a question in the chat from Ali Suleiman. He's asking, I have a question for Fatima. You said the total energy can be expressed in terms of wave function. Can you please explain this once again?
Then we leave the stage to Fatima. Yeah. So, is there any other question for me? No? Is it everything clear? Or are you completely lost? Which of the two? Guys,
maybe they are hungry.
Are you?
It is already the time of breakfast.
Are you ready? Are you still with us or not? Hello?
Participants.
Everything is clear for me.
Okay.
Thank you. Thank you, Matteo.
Thank you very much.
It's all clear? Unbelievable. Congratulations. Then I stop sharing and I leave the stage to Fatima.
We will come back to you again. I just answer my questions and I let you to share again. Then we sync again for some questions for you, okay? You can't hear?
I have to mute myself.
If you're talking, we can't hear you. I think you need to unmute yourself.
We can't hear you, Fatma.
We cannot hear you, Fatima. Still. Fatima, we cannot hear you.
I'm not sure if she can hear us. Can you hear us, Matteo or Fatima?
Matteo, we cannot hear Fatima. Can you hear us? No.
I think they don't hear us. Let me maybe raise my hand. Or send her a message. Let me send her a message. لغة الإشارة يا
We cannot.
We can't hear you. Fatma,
we cannot hear you. The sound. We cannot hear you. Yes, we cannot hear Fatima. The sound is not there.
I think she can't hear us as well.
Yeah, I don't think she
It seemed like he also was a man.
Yes.
Oh my God. After all this, they are not hearing.
Okay, now we can hear you.
I was talking a lot.
We just hear you.
Finally.
Okay,
but we were trying also to make a
but maybe you heard me through Matthew's. He's muted. Okay.
Yes, he's muted. So.
Yeah. So
there is 2 questions were in the chat.
Yes, I was already answering the questions and
if you can repeat again. So the first question was by Abu Adam. He said, explain how the total molecular wave function is separated into electronic and nuclear wave function.
I was already explaining that. Okay, so okay, maybe I start from the beginning. Okay, so we have the Hamiltonian here. Okay, the many body Hamiltonian. I said that it contains a kinetic energy of the electrons, which is given by this term here. Okay, Te. Okay, and another term which it's for the kinetic energy of the nuclei, which is given by this formula here. Okay. And then by having this idea that electrons are much lighter than the nuclei, their mass is much smaller than the nuclei, then we can see that the kinetic energy of the electrons are much higher than the kinetic energy of the nuclei. Then what Born Oppenheimer suggested is that since we have this mass of the electrons that are much less than the mass of the nuclei, we can write our wave function, which is a function of the set of space coordinate of the electrons and space coordinate of the nuclei. For us, we would like to simplify the problem more, okay? Then we can write this function in terms of two functions. A function that depends on the set of coordinates for the electron, and another function that contains the set of coordinates for the nuclei, which are capital Ri, okay? And we have also Ri is still here, okay? Then if we take out this expression and we put it back in the Schrödinger equation here, then we can simplify this Hamiltonian. There will be, when you can do also this derivation yourself. If you do that, take this wave function here and put it back in the eigenvalue and then try to calculate this, then we will find that there are some the kinetic energy terms of the nuclei that will be acted on the wave function of the how to say it, of the electrons, that we will cancel out these terms, okay? And then because the kinetic energy of the nuclei is very small, okay, then the derivative will be neglected, okay, when we take the derivative on the wave function. Then we can simplify the full equation into or this will help us to decouple the problem into two equations. One equation that have more information for the nuclei or the quantum nature of the nuclei, another equation that has more information for the quantum nature of the electrons, because we have here the how to say, the kinetic energy of the electrons, okay? And then but we still also have the coordinates of the nuclei. But what we do is to solve this equation for a fixed position of the nuclei. So the nuclear parameters, or which is a set of Ri here, or Ri, enter as the fixed position for the electron. So for a given position of the nuclei, we have the, let us say, the distribution of the electrons or the quantum nature of the electrons. I hope this is clear, okay? And then another question was about the functional, okay? So this is just a definition, okay, for a functional, okay? The definition of a functional is that we have a functional, this is a function that the input is a function, okay? And the output is a number. So if we want to calculate, for example, the energy, okay, which is at the end is the eigenvalue, is just a number. The energy that we are going to get out of this expectation value is just a number, okay? So if we have the wave function, which is a function, okay, and then we need this input, okay, in order to calculate this, in order to get this energy out of here, okay? So it's just like we know the expression for the operation, for the operator, for example, this O hat that we have here. In order to get this number, which is the expectation value of this operator, we need to calculate this integral, for example, if we have the wave function. So our input in this case is a function. That is why we call it a functional, okay? So this is the input. So we need psi in order to get this, just like we did for the harmonic oscillator here, okay? When I calculated the the expectation value, for example, for the t operator, then what we needed here, we had the expression for the operator, we needed the psi, okay, that we have here psi in order to calculate t, and at the end t is just a number, okay? So
thank you so much, Fatima. If there is another question we can take. Before taking a question, I want to ask Professor Matteo and Fatima if you can share the materials with us.
I did already
The
share
slides.
the slides on the drive that you have sent the link.
Sure, I can share what I wrote.
Yes.
Yeah. Thank you. Thank you so much. Any question from the participant? If there is no question, we usually, after the finish of the lecture, we take just a screenshot, final screenshot.
Yeah.
Abu Bakr, can you make a screenshot?
Everyone
Actually,
should
I forgot yesterday.
Yes.
It's good that you reminded us today.
So everyone should open the camera, and then we are going to take a photo, right? So everyone should open the camera.
Yeah, if it's possible, but
yes, if they want, they can open there.
Okay. 1, 2, 3. Okay, another one. Okay, that's it.
Okay, thank you so much, participants.
Okay,
And also
thank you so
the
much.
lecturers.
And good luck with the rest of the school. Yeah.
Okay.
I will prepare for some lectures, maybe. Yes.
Thanks.
I'm sorry that
you
I'm
so
not
much.
opening the
Thank
camera
you so
because
much,
I'm not ready
Professor.
for this photo. Sorry for that.
We can take one additional one first.
Okay, thank you.
Okay. Yeah, thanks a lot, Prof. Matteo. Thanks a lot, Fatima. It was very detailed and very nice lecture. I would also like to thank all the participants. Thanks, Ala, for the great moderation of the lecture. I have a couple of announcements. First, I would really like to welcome the Palestinian students, and please feel free to interact and ask questions. Maybe for the other participants, they are interacting before you, so they feel more comfortable. But please, this is an invitation for you to feel comfortable also and try to interact during the lectures. For those who are attending with us also the tutorial session, Dr. Musa has a proposal that we can make a pre-session tomorrow at around 4, just to revise all the installations of the tools. So anyone has problem in installing the tools and any technical problem, we can organize a session for 1 hour at around 4. I will also try to update you in our WhatsApp community. Yeah, I think that's all from me. Thanks a lot, all, and
So I have a question.
Yes.
The same Zoom link will be used for the entire school, right?
Yes, it's a really recurrent link, so
Okay.
feel free to.
And you're welcome to also attend with us.
Yeah, maybe.
Yes, thanks a
So
lot.
I would like, if there is no question from the participants, I would like to conclude the lecture of today. It was a real honor and pleasure to have you two here with us. Thank you so much, Professor Matteo, for the explanation, a very detailed explanation and advice. Thank you so much, Dr. Fatima Yahya, for also the advice and for the lectures. Thank you all participants from Sudan, from Palestine, and also the members of the Photon Center. And see you tomorrow at 9 for the next lecture. Thank you so much.
Many thanks to all of you. Bye.
You are muted. Yeah.
Bye.
Thank you, Matteo.
Thank you.